Dear students, welcome to the online class. I am Dr. S.S.C. Hiremat. In this video, you are going to study about the heterogeneous catalysis, in that the bimolecular surface reactions. Bimolecular means there are two reactants in this reaction. Suppose A is a reactant and S is the surface or the catalyst, and it forms one intermediate complex, that is AS, with rate constant K1, and AS dissociates to give back the reactant and surface is freed with rate constant K minus 1. Let us number this equation as 1. Then another reactant B reacts with surface and forms another intermediate complex BS with rate constant K2. Then the BS dissociates to give back the reactant B and surface is freed with rate constant minus 2. Let us number this equation as 2. Then the intermediate complex, that is AS, reacts with another intermediate complex, that is BS, to give the product, and the S, that is surface, is freed. Surface is given out, and this reaction takes place with rate constant K3, that is K3. Let us number this equation as 3. Now we can apply the steady state principle to the intermediate complex AS and BS. Applying steady state approximation to AS and BS, we get, that is dAS divided by dt is equal to, here AS is formed by this reaction, that is K1 into concentration of A into concentration of S, and AS decomposes back by this reaction, that is rate constant K1 and concentration of AS, and this intermediate complex reacts with BS to give the product. Thus that is K3 into concentration of AS and concentration of BS. Okay, this is equal to 0. This is one equation. Okay, similarly we are going to get another, that is ABS divided by dt is equal to K2 into B into S minus reciprocal of the reverse of this, that is K minus 2 into BS minus K3 minus K3 into AS into BS. Okay, this is equal to 0. We are applying the steady state principle to this. Let us number this reaction as 4 and this reaction as 5. Okay, suppose theta A, that is fraction of the total area vacant, that is the fraction of surface area vacant, that is theta V is equal to, theta V equal to 1 minus theta A minus theta B, that is theta A, that is fraction of the surface area covered by AS is equal to theta A. Then similarly fraction of surface area covered by BS is equal to theta B, the theta B. like that, the theta phi is the vacant surface area, theta A is the surface area covered by AS, and theta B is the surface area covered by this. Okay, thus we can apply the steady state principle to this. That is, surface area, vacant surface area theta is equal to 1 minus theta A minus theta B. Okay, one equation. And another one is the surface area covered by AS, that is surface area covered by AS is, that is theta A, surface area covered by BS is theta B. Okay, now we can rearrange this equation, that is K2 AS, K minus AS and K3 AS. Okay, here that is surface area covered by this AS is represented by theta phi, which is proportional to theta B, and that is CS is the constant. CS is the constant. Okay, similarly, surface area covered by AS is equal to theta A and constant CS, and surface area covered by BS, that is BS, concentration of BS equal to CS into theta B, theta B. Okay, means the three sides is equal to vacant surface area multiplied by the number of sides per unit area. Then surface area covered by AS equal to the total area covered and number of sides per unit area. In this way we can calculate this. Let us substitute the values in these equations. Okay, now this equation becomes, equation 4 becomes, equation 4 becomes that is dAs divided by dt, dAs divided by dt is equal to K1A, and what is S? CS theta V, CS theta V minus K minus 1 AS, that is minus K minus 1 AS equal to CS theta A minus K3 into AS, that is equal to CS theta V, AS equal to theta A, that is theta A, and CS into theta B, means concentration of AS equal to theta A, concentration of BS equal to theta B. Now when K3 is very small, very small, then we can neglect this. Then this becomes dAs divided by dt equal to this term is neglected. Okay, then here we are making this equal to 0, as it is made equal to 0. Then we may write K1A, and here also CS gets cancelled. K1A theta phi minus K1 theta A. Okay, that is equal to 0. Okay, thus we can rearrange this, that is theta A equal to K1 A into theta V divided by K minus 1. Okay, K minus 1. Okay, and it is equal to 0, we can rearrange that. that theta A equal to this divided by this. Thus we can rewrite this, that is theta A equal to, we can substitute K1 divided by K minus 1 by capital K1 into A, concentration of A into theta P, theta P. Okay, that is equation 5, and suppose this is equation 6. Equation 6. Now, similarly, we can substitute the values of this in this equation. In this equation, thus we are going to get that is d bs divided by dt is equal to, suppose that is part K2 into B into S, that is K2 into B as it is, okay, and S is equal to CS theta phi minus K2 K minus 2 into BS equal to CS into theta B minus K3 into AS equal to theta A, that is CS theta A and CS theta B. Here CS is the total number of sites per unit area. Okay. Now when K3 is very small, then this term gets cancelled. Okay, we can neglect that. Then we can make this equal to 0. This is equal to 0 means this is equal to 0. Then here this CS and this CS are cancelled. Thus we are going to get d bs is equal to divided by dt equal to, okay, that is K2 into B into theta V minus K minus 2 theta B. Okay, on rearranging this, we are going to get theta B equal to K2 divided by K minus 2 into B into theta V. Suppose this is equation 6. This is equation 6. Okay. Now theta A, theta B, we got the values. Then from equation 3, you can remove this. Okay. Back from equation 3, rate, that is rate is equal to d, that is d product, okay, divided by dt. This is equal to K2 into theta A theta B. Okay, this is same as K2 into concentration of AS and the concentration of BS. Concentration of AS into concentration of BS. Okay, thus we can write rate is equal to that is K2 into theta A equal to K2 into theta A equal to capital K1 into concentration of A into theta P. Okay, then into theta B equal to capital K2 into B into theta phi. Okay, this is equal to, we may write K2, that is small, K3, not K2. This is K3. These are all the third equation. Okay, that is third equation, rate equal to. Okay, that is K3 into capital K1, capital K2, concentration of A and concentration of B. Okay, this is equation 7. This is equation 7. Now we want to substitute, that is theta A, theta B and theta phi square, theta phi square, theta phi square. Okay, now let us this equation by 7. Okay, now we can substitute this reaction, that is here theta phi equal to, this is theta phi, 1 minus theta A, theta B. Theta V equal to 1 minus theta A, theta B. Okay, we can remove this, so that theta V equal to 1 minus theta A means, theta A means K1 A, that is K1 A into theta V. Theta B means K2 B into theta phi. Okay, theta V. Now we can rearrange this, that is 1 equal to 1 this side, suppose all these are taken this side, that is theta V minus K1 A theta V, minus becomes plus, plus K2 B into theta phi, theta phi. By taking this common, that is theta phi into bracket, that is 1 plus K1 A plus K2 concentration of B and lower bracket. Okay, then we may represent, that is theta phi equal to 1 divided by 1 plus K1 A plus K2 B. Suppose this is equation 8. Equation 8. By substituting the value of theta phi, this is theta phi in equation 7, we get, that is from equation 7 and 8, from equation 7 and 8 we get rate is equal to K3 K2 capital K2 capital K1 capital K2, concentration of A and concentration of B. Okay, concentration of A into concentration of B. Then theta phi square means 1 divided by this. This is equal to 1 plus K1 A plus K2 B, that is K2 B. Okay, this is one form of the rate equation for the bimolecular reaction. Now we can substitute the concentrations by pressure in the case of gaseous reactions. Okay, that is concentration of A equal to Pa and concentration of B equal to Pb. Concentration of A equal to Pa, concentration of B equal to Pb. Then equation 9 becomes, okay, then equation 9 becomes, that is rate equal to K3 into capital K1, capital K2, then A PS B PB divided by 1 plus K1 PA plus K2 PB whole square. That is equation 9. Equation 9 and this is equation 10. Equation 10 is the expression for the rate of bimolecular surface reaction in terms of pressures or partial pressures. Here it is in terms of their concentrations. Okay, this is the rate equation. Then we can apply the conditions, that is extreme conditions. We can apply the extreme conditions for this reaction. That is when that is first condition, when K1 PA plus K2 PB is very smaller than 1. Very smaller than 1. Then what happens? This is neglected, and remains the same. That is rate is equal to K3, K1, K2, PA and PB. Okay, means rate of this is one constant. All these are the constant directly proportional to two pressure terms or concentration terms. Then the reaction becomes second order. Okay, second order means order with respect to A is 1, order with respect to B is 1, then totally the reaction is second order. Then second condition, when K1 PA, that is 1 K1 PB is 1 plus K1 PA, that is 1 plus K1 PA is very larger than K2 PB. Then we can neglect this term. Then the equation becomes rate equal to K3, K1, K2, PB, PA into PB divided by 1 plus K1 PA square. Thus the reaction is first order with respect to B, whereas it is fractional order with respect to A. That is less than 1 order, that is fractional order. Then the reaction becomes first order with respect to, that is B, that is PB or B. Okay. Then another condition, that is when both are neglected. Another condition, that is third condition, such that PA, K1 PA plus K2 PB is very smaller than, that is K1 PA is greater than this, negligibly small, this is larger, and K1 PA is larger than 1. In the both means both are negligible. This as well as this one is negligible and K2P is also negligible. Then what happens? Equation that is 10 becomes the rate equal to K3 into K1 into K2, then PA PB divided by this is neglected, then you are going to get only K1 PA, okay, that is square, K1 PA square, that is rate equal to this K1 square and this K1 gets cancelled, then K3 K2 divided by K1, okay, then PA square is there, 1 PA is there, then you are going to get PB divided by PA. Then in this case, order of this reaction is 1 with respect to PB and with respect to PA is -1, that is negative order. Means then the reaction is the reaction becomes first order with respect to B, that is PB, okay, with respect to B, that is PB, and negative order with respect to, that is A, negative order with respect to A, means with the increase in concentration of the PB, rate increases, that too with power 1. Therefore, order with respect to B is 1, whereas order with respect to A is -1. Means with the increase in concentration of B or pressure of B, rate increases, whereas with increase in concentration or the pressure of A, rate decreases. Means order with respect to A becomes negative and order with respect to B becomes 1. Okay, this is about the kinetics of bimolecular surface reactions. This is the rate expression and these are the conditions. 3 conditions.